What's up? This is lab number 5, the big rope swing by me, Paul Cotter. What's good? So the goals for this, we're going to use Newton's second law, which is F net equals dp dt, to predict motion with a non-constant force. Our forces that make up F net are Fg and Fs, where Fg is negative mg in the y direction and Fs is negative ks. Negative ks is going to be acting in x and y, not z, no z on this. And then F net is going to equal Fg plus Fs. And then I'm going to make a program in GlowScript to model the motion of the swinging and predicts the maximum velocity. So some continued goals, we're going to use the energy principle, which is delta E equals delta K plus delta UG plus delta US. Then we're going to predict the motion and energy with that. And so the formulas for that, right? Delta K is the change in K, 1/2 mv squared. Delta UG is the change in UG, mgh. Delta US, 1/2 ks squared. Bang. Our system, right? So we're going to be using a person. My mass is around more like 72 kilograms because I'm like a skinny queen. But we're just going to use 75. And the rope is a bungee with K equals 155. And it's determined by iterating the GlowScript model to match real life video. And the rope is 150 feet, which is again determined through GlowScript. Here's my code, right? There's everything else is just like initializing the model, but this is the important stuff. So first we're going to calculate the L initial, which is the position of the ball minus this position of the spring. Then we're going to go to L hat and S. Then we're going to use our formulas for K, UG, US, and E to get some initial conditions down. From there, we're going to go into our loop, which is going to actually be doing the model. So each iteration of delta t is going to be going through this curve or this code one time. So as you can see, you're going to calculate the force of gravity at each given point, the force of the spring at each given point, and the F net at each given point, and then you're going to use that information to find the velocity here, and then use that information to find the new position for each time. Associated with that, we also have different L's, which are the angular momentums, and that's also the spring axis. And then these are the final, these calculations here are for the final energies and the final gravities at each point as compared to the initials. And then you're going to calculate that change, which is the final minus the initial, and then finally plot everything down in our graphs, which look like this. This is our motion graph. This is just like what the motion looks like after the model has run. Next up, the X position and the Y position, right? So as you can see, the bottom of the ground would be at -20 here, just because the frame of reference is different. But in the video, it says that it should stay about 10 feet above the ground, which it does. As you can see, there's around 10 feet before it hits the ground, which is good. And then our X position starts at -15, goes up to 20, right? The bungee kind of escalates it along there to make it move forward. And here is our energy graph, right? So as you can see, as one goes up, the others go down, so that we are in equilibrium, right? Delta E is not changing; it's a flat line at 0. The maximum velocity is 6.3088 meters per second. No, it's 16.088 meters per second. I think. And then the max spring force is 2144 newtons at those times. The motion, right? It's a constant summation of the forces acting on the person gravity, spring, and drag. And a net force does exist. Some improvements, we could include the drag force. Actually, we didn't actually include it, right? And increase the accuracy of data using a better tracking program. And that is all.